All right, so now on expectation of joint distributions, and we would like to begin with the expected value of PMF or probability mass function. Okay, so let f of x, y denote the joint PMF of the discrete random variables x and y, and let h of x, y denote a real value function of x and y. Okay, so then the expectation of this real value function can be expressed as shown in equation 12, provided that this condition exists. Okay. And let's take an example. So the table below gives the joint PMF of x and y, and want to find the expectation of x squared y, okay? The product of this. So let's take a look at the solution. So expectation of this can be expressed in this form with sum over the origin of x and y, okay? Let me quickly show you this. So these are the possible values for x, and these are the possible values for y. So we square this, okay, by the expression here. We square this, multiply by the value of y, and take the corresponding joint PMF. We square this, multiply by this, and take the corresponding joint PMF. We square this, multiply by that, and take the corresponding joint PMF. We square this one, multiply by that, and take the corresponding joint PMF. Okay, that's basically what we're trying to do. So here we go. Right, so once you use your calculator to compute this, you obtain this. Okay, very quite simple. All right, so now let's take a look at the expected value of PDF. Let f of x, y denote the joint PDF of the continuous random variables x and y, and let h of x, y denote a real value function of x and y. Then the expectation of this real value function can be obtained in this form. Okay, now we take a double integral of the product of our real value function together with our joint PDF. Okay, provided that this condition also exists. Okay, so let's take a look at an example. The random vector xy has the PDF shown below. I want to find the expectation of the x and y. Okay, so how do we do this? So the expectation of xy can be expressed in this original formula. So I want to take the integral with respect to x before with respect to y. Okay, so let me show you. Okay, so we know the expectation of the range for x is from 0 to 1, and that y is from 0 to 2. Okay, this for x 0 to 1 and y is from 0 to 2. So that's basically what we have here. And these are real value function, and these are joint PDF. So once we try to multiply through by this real value function, we obtain this. Now we can take the integral with respect to x. Okay, once we do that, we obtain this. So we try to input the values, you obtain that. Okay, now we can take the integral with respect to y. So once we do that, we obtain this, and once we input the values, we also obtain this, which is very quite simple. Okay. All right. So now let's jump into some properties of expectations. Theorem 1. Let x1, x2 up to xn denote n random variables, and let c1, c2 up to cn be constant. Okay. So then the expectation of the sum of the product of the constant and the random variables can be expressed in this form. Okay, so we just have to pull the constant out so that we can take the expectation of the random variables. Okay, all right. Now another theorem, theorem 2. Let x and y be two random variables with expectations e of x and e of y respectively. Then the expectation of this random variable x and y, the product of it can be expressed in this form as shown in equation 15. Okay, where the second term on the right hand side, this term here, is called the covariance of x and y. Okay, we'll take a look at this very soon in our subsequent tutorial. Okay, this defines the covariance of x and y that can be denoted in this form. Okay, so take a look at kindly take notice of this theorem 2. So if x and y are independent, corollary 1, if x and y are independent random variables, then the expectation of the xy can be obtained as the product of your individual expected values. Okay, so this is coming from theorem 2. Okay, once these two random variables are independent, this covariance will go to 0. So we just So we just have only this expectation of x and y. This will go to 0, okay? So the corollary 1 is coming from theorem 2. Now theorem 3, let x and y be two independent random variables, and let g of x and h of y be real value functions of x and y respectively. Then the expectation of the product of this real value functions, g of x and h of y, can be expressed in this form coming from corollary 1, okay? So if they are independent, then you can also have it in this form. All right, so now on conditional expectation. So let x and y be a two-dimensional random variable, and let g of x be a function of x. The conditional expectation of g of x given y is defined by equation 18, provided that if these two are jointly continuous. Okay, once they are continuous, we use this expression. And if x and y are jointly discrete, then we're going to use the expression in equation 19, where the summation is over all the possible values of x. Okay, so take notes of this. Remark: the conditional variance of y given x is given as shown in equation 20. Okay, so that is the conditional variance of y given x. So if x and y are discrete, we use this first case here. And if x and y are continuous, we are going to use this second expression here, okay? And also the conditional variance of x given y is given by equation 21. So when x and y are discrete, we use this first case here. And if x and y are continuous, we are going to use the second expression here, okay? So let's take an example. You will realize that this is very quite simple to do. So using the information from examples 1 and 6, I want to find the expectation of y given that x is equal to 1. So if you have maybe escaped these two examples, you can check it out by clicking on the link in the card above, or check the description of this video for the link, okay? All right, so now let's take a look at the solution. So from example 6, we obtain this, okay? Now I want to find the expectation of y given that x is equal to 1. So basically, we're going to multiply this, take the product of this and that, and add it to the product of this and that, and add it to the product of this and that, okay? So here we go. So we obtain this, okay? And once you calculate this, you obtain this. Very quite simple. All right, now let's take a look at another example. The continuous random vertex y has the PDF defined below. So I want to find the expectation of x given that y is equal to a particular value of y, okay? So how do we do this? First, we have to find the marginal density of function of y, okay? So we know to obtain the marginal density function of y, we have to take the integral of our joint PDF over the region of x, okay? So that's what we have here. All right, so this is going to be the range for x from y to infinity. Let me show you. So you can see that x is greater than y and y is greater than 0. So the possible values of x can be from y to infinity, okay? So that's what we have here. So once we take the integral with respect to x, we obtain this. And once we, sorry. And once we try to input the values, we obtain this, okay? All right, so now the next thing is to obtain the conditional PDF of x given y is equal to y. And this can be expressed in this form. So we input the values and we obtain this, okay? Very quite simple. So now our main focus or our main objective is to find the expectation of x given that y is equal to y, which can also be obtained by using this expression here. So we have the range for x to be from y to infinity. We have our x multiplied by the conditional PDF of x given that y is equal to a particular value of y, which we have here. So once we try to multiply through, or we can express this in this form, okay? So we just put the expectation, the exponent y out, okay? Once we try to multiply through, obtain this, so we can pull the exponent y out so that you can have everything with respect to x. All right, so we know that this looks like the product of a transcendental function together with some polynomial function. So we have to use integration by part, okay? So we'll use integration by part. We'll let u to be equal to x and the v to be equal to u minus x, okay? The exponent of that. So the u will be equal to the x and then it can be expressed in this form. So use integration by parts, we have this expression, okay? So if we try to use the integration by parts, we obtain this, okay? So this is our u v, right? The product of u v, and this is v du, okay? So once you try to input the values, you obtain this. Once you try to integrate this, you obtain that. So we can multiply through by exponent ui, okay? So once you try to multiply through, you obtain this, and you can also obtain this once you try to compute this. This will be similar to that, okay? Y plus 1. Very quite simple, okay? All right, so this is a track question. I'll leave the solution in the description of this video so you can check it out. Please, if you find value into this tutorial, don't forget to subscribe if you have not. And thank you for watching.